Okay, good morning. Last time I think we have talked about condensation polymerization, and we have summarized the Carrodus equation where you have bifunctional monomers present in your monomeric system, and two of those functional groups will react together to have a byproduct, so that the condensation polymerization will result in this type of equation right in here, where the M is the monomer concentration. Initial monomer concentration is M0, and monomer concentration at a given time t. So after your monomers are reacted, and at a given time t, of course, the monomer concentration decreases, and those concentration at a given time t inside of the reactor is defined as M, where M is expressed as initial number of molecules times the fraction that was reacted. Okay, is P, and the 1 minus P is the fraction that is left in your system. So if you multiply the initial number of molecules times the fraction that is left in your reactor, then you can come up with the concentration at a given time t of your functional groups. You knew that the degree of polymerization is defined as initial number of molecules, N0, divided by the number of molecules that was left in your reactor, which is the same as M0 divided by M. Then you come up with a very simple equation of finding the degree of polymerization, whereas this is 1 over 1 minus P, by knowing this equation. So this is well-known Carrodus equation, assuming that you have bifunctional monomers, right? So you have two functional groups that is present in your monomeric systems. If you have three functional groups, what happens? Okay. So we have to come up with the different equation in the next slide. But before we go to the next slide, I think last time I have emphasized that the degree of polymerization, around 200, will be regarded as a polymer that imparts enough or sufficient mechanical properties of your polymeric systems, right? So around 200 of dPn, then your molecular weight is high enough to give you a polymeric systems. So in order to have a dPn of around 200, you have to have about P is equal to about 0.995, meaning that 99.5% of your monomer should have reacted already. Okay, so the 99.5% of your reaction is very efficient reaction. So you should not have any side reaction in order for your condensation polymers to become real polymer. Okay, that's the essential summary of what we have done, and I just wanted to come up with the generalized Carrodus equation down in the bottom here, and in conclusion, dPn is equal to 2 divided by 2 minus Fp. Okay, if F is equal to 2, then you come up with just Carrodus equation that we have just defined. Okay? Now, it's not that difficult, but the difference between this generalized equation and just a simple Carrodus equation is 2 and F. So we will know why we have a 2 here in the brackets, or in this numerator or denominator, and F. Okay. Now, let's define again the extent of reaction P. Extent of reaction P is actually if you go back, P is defined as extent of reaction, meaning that the monomer that was consumed. Okay? If P is equal to 0, then you do not have any monomer that was consumed. So you have a hole of your monomer that was left. If P is equal to 0.5, meaning that you have a 50% of your monomer that was consumed, right? What about 1 minus P? 1 minus P means the monomer that was not reacted at all. Okay? 1 minus P means that your probability of finding your monomer that was left. Okay? So 1 minus P means, I said, the monomer that was left in your reaction system. P is defined as the monomer that was reacted, right? So P and 1 minus P is related with the monomer you can find in your polymeric systems. Okay, the P, again, let's say that instead of monomer, let's say we have a functional groups. Okay, because we do not know whether this monomer has 2 functional groups or 3 functional groups or 4 functional groups. Let's say that let's define the extent of reaction not in terms of number of molecules, but in terms of the functional groups. Okay, so that way we can generalize them. So P is defined as number of functional groups that was consumed. Okay? Divide by number of functional groups initially present. Well, if you define F as a number of average functional groups per monomer, okay, number of functional groups of your monomer, if F is equal to 1, you have a unifunctional monomer. If F is equal to 2, you have 2 functional groups in your monomer system. If you have a glycerol, then you have 3 functional groups. If you have a benzene ring or phenol, I think we have talked about the phenol last time, and you have 2 ortho-positioned functional group and 1 para-positioned functional group. So overall, you have 3 functional groups. Okay, and you may have a tetrafunctional, pentafunctional, stuff like that. So F is just a general number of functional groups of your monomer systems. N0 is the initial number of monomer. So N0 times F is number of functional groups that is initially present in your system. Okay? N0 times F. N is a number of final molecule, number of molecule that can be found in your after reaction time T. Okay? After 1 hour, after 30 minutes later, your monomer has already consumed, but reducing the deduction of your the monomer system that was reacted is an N, okay, which is the number of final molecule. So let's say that number of functional groups initially present is what? Number of initial groups that was present, N0 times F. And number of functional groups that was used is N0, which is initial number of molecules, times functionality, F, minus N, which is number of molecules that was left in your system, times F. Okay? So N0 times F minus N times F is the number of functional groups that was used. But instead of F, we have just put 2 here, and I just wanted to ask you why we have instead of F, we put 2 here. Why we have a 2 instead of F? It's a very simple question, but very meaningful. Now, this is the initial number here in the denominator, whereas we have functional groups that was consumed, or reacted, or used. Okay? Remember that in the Carrod's definition, we have to have two functional groups to react. Although you have many functional groups in one system, let's say that we have 10 hydroxyl groups, and we only have two carboxylic acid groups. What happened? One carboxylic acid will react only one hydroxyl group. The other hydroxyl group will react one more hydroxyl groups. So you have all the carboxylic acid groups that react already. It doesn't matter how many of our excessive hydroxyl groups there is present. Okay, the only functional groups that is reacting between the carboxylic acid and hydroxyl group is just one by one. Okay, so two functional groups, one of each, participate in the reaction rather than multiple reactions. Okay, so we don't need the F in this case for defining the consumption of your monomer or reaction of your monomer. So we just have a 2 here. Okay, it's very simple, but you have to realize your reaction system. So 2 times N0 minus N divided by N0 F is the extent of reaction. And dPn is defined as N0 divided by N. So if we manipulate this equation here, P, extent of reaction P, where N0 divided by N is equal to, well, here in this case, the extent of reaction P is defined as 2 divided by F minus 2 divided by dPn F. If you rearrange them, you come up with the final generalized Carothers equation, where 2 divided by 2 minus Fp. Okay? So 2 divided by 2 minus Fp is just a general equation. Simple, but considering your number of your functional groups in your polymeric systems. If F is equal to 2, meaning that you only have a bifunctional monomers, then dPn is equal to 1 over 1 minus P, which is exactly the same as what we have just seen. But let's say that we have other systems. Okay, let's say that we have we have 10 monomeric systems. If the functional group is equal to 20, okay, meaning that this is the bifunctional. If you have 2 functional groups in your monomer systems, your functional group is number of molecules times or multiplied with the number of functional groups in your monomer systems. So your final functional groups, the initial functional groups that is left is about 20. If we assume that we have a final molecules, which is 2, that means that your 80% of your monomer has already participated in your polymerase systems. So P is equal to 2 times the initial N0 minus N divided by F N0 times F. Okay? So it comes up with about 0.8, meaning that you have 80% of your monomer that was already participating in your systems. But dPn in this case is only 5. Now I put here SU and RU. Can you guess what the RU and SU? RU is defined as repeating units, and SU is defined as structural units. Let me define what is the SU and RU. You all remember that Can you name this polymer? Nylon 6 or polycopperactam, right? So from your copperactam, it will be ring polymerized to become a nylon 6. Now, what is the repeating units? Repeating unit is in between the brackets, right? So this is all repeating units. So let's say that this is repeating units, RU. What if we have nylon 6,6? Nylon 6,6, right? Repeating unit is in between your brackets, right? So this is total, again, is repeating units. Now, structural unit is one monomer and the second monomer. Structural units. So we have two structural units in one repeating unit in the case of nylon 6,6. But in the case of nylon 6, structural unit, and repeating unit is the same. So structural unit is defined, is the one monomeric units that is participating in your polymerization system. But if you have two monomers, okay, AA and BB type, then you have two structural units in one repeating units. If you have AB type of your monomer, just like in the case of amino acid or in the case of copperactam, copperactone, stuff like that, then you have one structural unit and one repeating unit, and repeating unit the same as structural units. So this is what I mean by this, and I will tell you later on what happened if we calculate the degree of polymerizations. So the structural unit and repeating unit could be the same or could be different. Okay, you could have a maximum of two structural units in one repeating unit in the case of AA-BB type, and the AB type of your monomer. If you're using those type of AB type, then repeating unit and structural units are the same. Well, once again, if we have 99.5% of your extent of reaction, or P is equal to 0.995, okay, I told you that we should have very efficient reaction in the case of polycondensation reactions or step growth polymerization reactions. In order to achieve this very highly efficient reaction, we should not have any side reaction. We should not have any side. If there is any side reaction, then you lose your extent of reaction. Okay, extent of reaction. Therefore, the molecular weight will not be going very high. Okay? Side reactions, such as the one here in this case. If I have this type of hydroxy alcohol, this is hydroxy acid. If you heat it up, because this is AB type of your monomer, you should have ester. If this monomer participates in the polymerization reaction systems, your hydroxyl will attack your carbonyl, so you lose your water as a condensate or a byproduct, and it becomes polyester, right? But if you heat it up, you may lose the CO2 here, so that it comes with the one hydroxyl group containing the monomer instead of participating in the polymerization systems. And this is regarded as a side reaction. If this side reaction occurs, okay, at high temperature, then what happens is that you come up with the one functional group left instead of your monomer, instead of your polymerization systems to proceed. So this type of side chain, the side reaction prohibits the highly efficient polymerization reactions. So side reaction, prevents your polymer to become very high molecular weight components. Monomer purity is very important. So you should have a very highly pure monomer before you put your monomer in your reaction systems. Okay? So purity of your monomer is very important. Now let's state the highly efficient reaction, absence of side reaction, high purity monomer are three very important requirements for the polycondensation to obtain your high molecular weight components. However, the final requirements, fourth requirement, is most important in your case as well. Exact stoichiometry or known stoichiometry is very important, and this is what I should explain a little bit more about this. Okay? Stoichiometry in Korean term, 당량 대 당량 반응이라고 그러죠. 당량 반응이라고 그래요. Well, stoichiometry, meaning that you should have a very known stoichiometry. You should know how many moles of your monomer that is put it in. Okay? Now let's say that in your system, well, we may have an AB type. We can have AA and BB type. We can have multifunctional monomers. Okay, you can have polyethylene terephthalate, or you can have polyester from your very simple systems. You can have a condensation reaction from your bifunctional monomers. So the ethylene glycol could become a polyethylene glycol, or it could become cyclic dioxane. Okay? If this happens, then you do not obtain the polymer, but you have just the monomer systems. Okay? If this happens, this is regarded as a side reaction, okay? From the polymerization point of view. Now, for this amino acid, if you have a condensation reaction, it becomes polymer. But if heated up and becomes a cyclic lactam, then this is regarded as a side reaction. Okay, so this is what happened in here, and let me see. So we have to have a very exact and known stoichiometry in order for your polymer to become very high molecular weight. Now, I think this point will be coming up later again. I think we will touch this issue again. Okay. So in order for the exact amount of stoichiometry, I should explain to you what happened, and very simple reactions and the kinetic equations. Kinetic equation, although it looks very complicated, it's not that complicated, and it's very simple. Now let's assume that we have a carboxylic acid and hydroxyl group reacting together to become ester with the kinetic constant K, and you may have a byproduct, which is water in this case, or it could be methanol if you have an ester interchange reaction. But we have a hydroxyl group instead of ester, so this reaction is regarded as a condensation reaction, and byproduct should be water in this case. Anyway, you can describe this the reaction equation with the known rate equation. Rate equation here in this case is that rate means time. Okay, rate means time. So the consumption of carboxylic acid, rate of consumption of carboxylic acid is described as minus d carboxylic acid concentration divided by dt. If you put minus here, this is the consumption of your monomer. If this is positive, then this is the production of something. Okay, so d minus d COOH divided by dt, which means that your consumption rate of your carboxylic acid is equal to rate constant K times the concentration of reactants of each case plus any catalyst that should have used. Generally, the acidification needs the acid as a catalyst. So acid concentration could be put in here if it's not negligible. Right? If it's a very small amount, then you can, of course, you can cancel this out. So it could be a very simple equation. Okay. And also, an assumption is that we do not have any strong acid catalyst concentration, so we can neglect this in this case. Let's assume that this acid concentration is negligible. Right? Okay, the acid here in this case is regarded as the K times acid is regarded as a K3, so that the rate of consumption of a carboxylic acid is equal to K3 times the COH to the square, where the acid concentration is the carboxylic acid concentration, so that it could be carboxylic acid concentration to the 2 times the hydroxy group. Now, hydroxy group concentration and the acid concentration is the same because we put equimolar concentration of your monomer systems, so that let's say that hydroxy concentration is the same as carboxylic acid, so it could be 3. If we integrate this equation, if we integrate this, the second equation, then it comes up with the 1 over the COH to the second is equal to 1 over COH to the second, of course, but you should have initial concentration and times and positive and plus the 2 times K3 times T. Although and assume that we have already defined as P, extent of reaction, is equal to 1 over n divided by n0, okay, n divided by n0, and you come up with the final equation if you put this P right in here. So 1 over 1 minus P to the square is equal to 1 plus 2 times initial concentration to the square to the rate constant times T. It's a little complicated in your case if you first look at it, but it's not that complicated. But we assume the equimolar concentration of the carboxylic acid and hydroxy group, and we put the acid as a strong acid to catalyze this reaction, and the integration of this equation will come up with a final equation. Now, this means that if we have a strong acid concentration, then it can come up with the simple equation right in here, because we neglect the acid concentration, and come up with 1 over 1 minus P is equal to 1 plus K2 times the initial concentration times T. Okay? Now, the equation here in this case, is a little different. These two equations comes from the different assumption, where the first equation is where we have a strong acid, which is not negligible. Second case is the acid concentration that is negligible in this case. Therefore, we know that dPn is equal to 1 over 1 minus p according to the Carrodus. Therefore, because we know 1 minus p here, or 1 over 1 minus p here in this case, is equal to 1 plus K2 times initial concentration. Okay? Okay. So by knowing 1 over 1 minus p, which is the dPn, we can rewrite this dPn equation from rate constant and time t. Okay? So we can calculate dPn as a function of time if you know rate constant Kt, K2. Or you can calculate the extent of reaction P and come up with the dPn. Now, so this equation is a rate equation instead of static thermodynamic aspect of equations. So you can calculate, if you know K2, you can calculate dPn at any time t. That means if you put your known amount of your monomer, AA and BB type of your monomer, and after time t, after 10 minutes, after 30 minutes, after 2 hours, after 5 hours, if you take some samples, or if you assume that that you have equimolar concentration, by knowing K2, because your degree of polymerization will increase anyway, you predetermine the dPn, which may be 200, could be determined by knowing your K2. Okay, so let's exercise in one equation. Okay, let's assume that we have a K2, which is 10 to the minus 2, here in this case, liter per mole sec, and let's say the C0, which is initial concentration of your carboxylic acid, C0, is equal to 3 molar concentration. Let's say that we have a dPn is equal to 50. Okay, that means we want to determine how long will it take to obtain the degree of polymerization of about 50 by knowing K2. Okay? Because we know the rate equation, which is dPn is equal to 1 plus C0 times K2 times T, and dPn is equal to 50. You know C0. C0 here in this case is 3 molar per mole sec per liter. Okay, 3, and K2 is equal to 10 to the minus 2. My question is, how long will it take? T. Okay, what's T? It's very simple. And what happened if I will decrease the rate constant from 10 to the minus 2 to 10 to the minus 4 in order to obtain dPn is equal to 50? Okay, only 2 order of magnitude difference in K2, then I think we may have a very different time scale. So for K2 is equal to 10 to the minus 2, reaction time takes about 30 minutes. Okay, 30 minutes. But if we have a very slow rate equation, rate constant, okay, 100 times less, the rate constant, it will take about 45 hours to obtain dPn of around 50. So anyway, from this exercise, we know that if you set up your target molecular weight, target dPn, and by knowing rate constant, you can determine how long will it take to obtain your target molecular weights. Okay? Okay? All right. So this is the one of the very important exercise that we have practiced. By knowing the Carrodus equation, and particularly if you know the kinetics of polymerization, we will be able to find out how long will it take to get the polycondensation, the reactions, by knowing the radiations and so on. So in this chapter, well, if you look at the textbook, whichever textbook that you may have, there is a kinetic section, polycondensation and kinetic equations. Those kinetic equations, is come up with the Carrodus equation, and they derive the concentration of your the monomeric system at a given time t, and by knowing initial concentration, you come up with the different the time scales, and at the end of your chapter, you have a lot of exercise problems. Okay? And in the second midterm exam, you're given in many types of your the problem sets, so that you have to know how you can calculate the degree of polymerization in some cases, or you're given the molecular weights, or you're given the rate constants, and various types of problem sets will be given as well. And I wish you can take those exercises, and I will give you in next time some of those problem sets as a homework. Okay. So the Carrodus equation that we have just talked about are the very simple Carrodus equation, but I wanted to describe this the rate equation and very simple Carrodus equation to be extended to explain about the molecular weight distribution. Okay, the molecular weight distribution is quite broad in the case of the polymer systems, and if it's very narrow, we know that we have a very narrow molecular weight distribution. And I gave you an example where we can obtain those narrow molecular weight distribution in the space. If you parameterize your systems without any gravity, then you can obtain the very narrow distribution. Whereas we in our atmospheric the Earth environment, because we have a lot of gravity aspect, we have a very broad distributions. So here in this case, we wanted to know about the number average molecular weight and the weight average molecular weight, and I wanted to describe to you how we can come up with these equations, the molecular weight distribution in terms of a number or in terms of weight fractions. Okay? So in this kinetic equations, we have to define that extent of reaction P is the fraction of the function groups. So the function groups, the fraction of the function groups that have already reacted at a given time t. So P is defined as the function groups that is reacted. 1 minus P is the probability of finding the functional groups after given time t. So that is left in your polymerization systems is 1 minus P. Okay. Let's define xmer. Xmer means your molecule at a given time t, after reaction time t, your molecule might be, you do not have only one molecule, but you have many molecules with different sizes, right? So let's generally define this type of the different molecular weight, different size, as an xmer. X could be 5 if it's a pentamer. S could be 2 in the case of dimer. S could be 10. S could be 20, 30, 50, stuff like that. So X could be any number. Okay? Those number represents how many repeating units that you have. Okay. Now let's say that you have xmer. Xmer contains X repeating units And at the end of your chain, you have functional groups left. You have 2 functional groups left. Okay? Now, for Xmer, we know that it has randomly selected polymer molecule containing exactly the X structural units. Structural units, X structural units could be defined as AA and BB type of your monomeric systems in your case. If you have a AB type, structural units and repeating units are the same, right? Now, let's say that we have X structural units, and we have amino acid case. We have the AB type of your monomer systems in the first case. Okay, so we have carboxylic acid. In the case of amino acid, we have 1 carboxylic acid in 1 monomer. We have 1 amino group in your 1 monomer systems. If you know the number of carboxylic acid after reaction time t, by knowing the end group analysis, we know how many molecules that was reacted. So X minus 1 is the reacted carboxylic acid or reacted amino acid groups. 1, we have one remaining carboxylic acid at the end of your chain, right? So the P here in this case is defined as the fraction of the functional groups that have already reacted at time t. So P is defined as the carboxylic acid group that has the 1 carboxylic acid group that was reacted. If you have 2 carboxylic acid that was reacted, the probability of finding the 2 carboxylic acid group in your polymeric systems is P times P. If you have a 3 carboxylic acid group of the finding the 3 molecules of a carboxylic acid group in your polymeric systems, you have to multiply this by P. P times P times P. Okay? If you have X minus 1 reacted carboxylic acid group, and the probability of finding those X minus 1 reacted carboxylic acid group, you have to multiply P times X minus 1 times, meaning that you have P times X minus 1. Right? P times X minus 1 means probability of finding the X minus 1 reacted carboxylic acid groups. 1 minus P means the carboxylic acid group, okay, of finding the unreacted carboxylic acid groups. So Xmer, the probability of finding the Smer in your system is that the probability of finding the X minus 1 carboxylic acid group that was reacted times 1 carboxylic acid group at the end of a chain, which means probability of finding Xmer is equal to P to the X minus 1 times 1 minus P, and is equal to Nx divided by N. Nx means the number of Xmer molecules divided by number of molecules that was initially present. I think this is N0 here. So probability of finding Xmer can be found as well in terms of the probability. Okay? Probability, because we have to treat this, a distribution in terms of the statistics. So Nx, probability of finding the Xmer, the number of Xmer molecule, Nx is equal to probability of finding Xmer, 1 Xmer molecule, times how many molecules of the Xmer, N. Okay? Because you have many molecules, okay? You count on each molecule, which is N, is equal to nx. N here in this case is defined as n0 times 1 minus p. So nx is equal to, if you replace this with here, it will become this reaction. So number fraction, the number of the xmer in terms of the fraction, number fraction is equal to n0 times p x minus 1 to the 1 minus p to the 2. So we have n0, which is constant. We know that the p is the extent of reaction, which could be variable. X could be, of course, the variable. And of course, the nx would be the variable as well. So if we plot nx here in the y-axis, and the x-axis could be the degree of polymerization, or x. X is how many molecules that you have. Okay, x could be number of structural units, or could be repeating units. Okay, in different way. So x could be plotted in the x-axis, and y here is nx. Because we have 3 variables in one equation, nx, x, and p, we can just reiterate the known equation, a known variable, where we assume that p is equal to something. If p is equal to 0.95 here, and you calculate the x versus the nx, then you come up with this line here. If p is equal to 0.98, then you come up with this line or this curve, 0.99 and 0.995, stuff like that. Okay? Now this represents number fraction of your xmer. Okay? Number fraction of xmer decreases. Number fraction of your xmer, decreases as you increase your extent of reaction. Extent of reaction, P increases. Okay, if P increases, NX decreases, but X increases. Now this looks very complicated, but it's not that complicated. If extent of reaction is low, okay, your molecular weight is quite low. Okay, small molecular weight component can be found many, but high molecular component is quite less. So you have small molecular weight fractions if you have a low P. If P increases, low molecular weight fraction decreases, but high molecular weight fraction increases. So you have a molecular weight distribution, okay, in terms of your number fraction and xmer. If we can describe this the molecular weight distribution in terms of weight fraction as well. Now this equation is for a number fraction, but we can describe this for the weight fraction. Weight fraction, the conclusion is that although this is very complicated equation, but I think I will explain to you a little bit, but the weight fraction is in the y-axis. This is the degree of polymerization, which is xmer, x. Okay? Weight fraction is a little different from the number fraction, but again, if P increases, then you can come up with the high molecular weight fraction rather than small molecular weight fraction if P increases. Right? Starting from 0.96, 0.9875, 0.999. The equation here is that weight fraction equation is given right here instead of a number fraction. You have x times 1 minus p to the 2 times p to the x minus 1. So if you plot Wx weight fraction and x here, and by assuming that p could be variable, could be changed or constant, then you can come up with this equation. Now this equation can be derived from the definition and of course the dPW definition, and by knowing somewhere around this equation that there is given, in the mathematical treatment, you can come up with these final equations. Now we know that molecular weight distribution is defined as dPW divided by dPn, and is equal to 1 plus P. P here in this case ranging from 0 to 1, so that it will become 2. So the one of the molecular definition of molecular distribution could be described here in this equation as well. Okay, now the equation looks quite complicated in your case, but in all of your textbook about the kinetics, you can find that this equation, this curve and this curve, which represents the weight fraction versus the number fraction, and you know that you can treat those probability of finding xmer in the statistical way of the definitions. Okay, let's go back to the equimolar reaction or stoichiometry. I think I will summarize the importance of those two equations after class, okay, in Korean, okay, so that you will better know what I'm going to say. Okay, now if you go back to your, the 4 requirements of the polymerization reactions, we have to have a very highly efficient reaction, and we should not have any side reaction. And third requirement is what? I think I forgot. Monomer purity is very important, yes. And fourth requirement is about the stoichiometry. Okay? Stoichiometry. So I would like to, come back to this issue. Now, with the molecular weight control. Okay? Now, you know that the time scale is very important, right? Time scale. In our definition of characteristic equation and rate equation, dPn, polymerization, is equal to 1 plus C0 times K2 times T. So if you control the time, then I think you will be able to find out the degree of polymerization. It took so long time if the K2 is low, right? It took about 45 hours if the K2 is 10 to the minus 4 in our case. But you will not be able to wait 45 hours to get the polymer, which is not very economical, right? So what happened? What you're going to do in order to control the molecular weight is, because the dPn is time dependent, yes, time will provide you high molecular weight, but you cannot wait. So what you're going to do is that instead of 45 hours to become dPn over 50, okay, although you sacrifice your molecular weight, if you cool down, if you quench your reaction vessel into your very cold water, then there will be no further reaction. Okay? There will be no further reaction if you quench or cool your reactors. And so, at a predetermined time, if you quench, then you will not proceed further reactions. So the reaction will stop and control the degree of polymerization and control the molecular weights. But there is one problem. Problem is that because you have a hydroxyl group and carboxylic acid group, okay, functional groups that is left, later on, if you heat it up again, then carboxylic acid group and hydroxyl group may react, right, later on. Well, this problem is because if you heat it up and cool down in the factory of manufacturing your polymer, then it will be shipped as a bead, Bead is like a rice, just like a small size of a rice. Your polymer is provided as a bead, okay? And in your bag, polymer bag, you have many beads of the polymer, and it will be shipped to your any polymer processing company, which produces this plastic, okay? In order to, for example, the S company or L company produces the polymer, polyester, but this company just produces the polymer itself, okay? Such as LG Chem or JL synthetic fiber or Samyang company, they produce only the polymer beads. Okay? But Monami, for example, they try to make this pen. Okay? Now they are different from the L company or S company, but this company, M company, tried to fabricate this shape of the plastic using their beads. Okay? So they buy these beads, polymer beads, and put it into the extruder, and they fabricate this, their own plastics. If you wanted to have this glass, most of this glass is made of polycarbonate or the polymethyl methacrylate, or even your plastic, the glasses as well. So you have to melt those plastics and extrude them to make your own shapes. Okay? Now, in order to melt your polymer, okay, polymer will be in the liquid phase at high temperature. At high temperature, upon melting, your carboxylic acid group and hydroxyl group may react again if you use this cooling method to make a bead. Okay? So if that's the case, your viscosity will change when you melt, so that it's not very desirable. Okay? So instead of using this quenching method, the second way of controlling the molecular weight is about the stoichiometry. So regulation of the monomer concentration is much more plausible way of controlling the molecular weight. Now, we use non-stoichiometric conditions. Instead of stoichiometric condition, we use non-stoichiometric conditions. In other words, we do not use equimolar concentration, but we use 1 molar excess, a little bit of excess amount of the second monomer. Okay? Let's say that what happened, what kind of trick that we use. Let's say that we have AA and BB type of your monomers. Now this monomer will come up with the polycondensation, of course, and you come up with if you put the excess amount of the second monomer, you come up with the rich in the carboxylic acid group at the end of your chain instead of hydroxyl and carboxylic acid group, where we knew that we have a hydroxyl and carboxylic acid group here in this case of cooling. So if you put one excess the molecules, then you have a same functional groups at the end of your chain. If you have a same functional group at the end of a chain, you will not be able to proceed further reaction, right? Even upon heating, even upon melting. Okay? Therefore, this is a very stable way of controlling the molecular weight, And we know that there is no further reaction. Even the M company buys and melts this polymer to fabricate into your desirable shape of your systems. So I told you that we have two ways of controlling the molecular weight. First one is about the quenching. Second is about the non-stoichiometry. But the non-stoichiometry is much more desirable than the quenching method. And the second method is very widely known, widely used in the industry rather than the first case. First case is very simple, but not very scientific. Okay? But second way is pretty much scientific. And I think I will show you later on how this method will determine the molecular weights. Okay? You know that the molecular weight is very important. Molecular weight determines the melting viscosity. If you have a high molecular weight, then you have high melting viscosity. Melting viscosity means that viscosity at a molten state. If you increase the temperature, your viscosity increases along with your molecular weight. Okay? If you have a high molecular weight, 한국말로 하면 엿 같은 정도가 더 심해지는 것이니까. But if you have a high molecular weight and high melting viscosity, it's very difficult to fabricate because you have a lot of resistance to flow of your the polymer systems. So we have to control the viscosity at a certain molecular weight. So molecular weight will determine your melt viscosity. Let's say how we can control how many excessive amount of your molecules that is needed in the case of non-stoichiometric systems. Okay? Let's assume that we have a feed ratio. Feed ratio is defined as Na divided by Nb. A means number of molecule that contains a functional group. Nb is number of molecules of number of the monomer that contains B functional groups. Okay? So Na divided by Nb is just a simple feed ratio. So we wanted to put this feed ratio into the Carrodus equation. Okay? And functionality F. So it will become little generalized equation of the Carrodus. So feed ratio is R. We know that P is the number of A functional groups that has already consumed at a given time T. If we define R times P, then this is the number of B functional group that has already consumed. If we put 1 minus P is the functional groups of A that is left at a given time T. 1 minus Rp is B functional group that is left. Okay? P consumed, Rp consumed of B, stuff like that. So number of unreacted A is number of unreacted A molecule is Na times 1 minus P. Number of the unreacted B could be Na times 1 minus Rp. What about the initial number of molecules? Because we have two functional groups at each end, assuming that we have a bifunctional group, number of the molecules, initial total number of molecules is Na times Nb, but because we have Na is defined as functional groups, you have to divide by 2. If you divide this by 2, then this will become the number of molecules. Na is a functional group number. Okay? So by knowing that, because we have your chain end, at the end of your chain, you have two ends. One end has one functional group. The second end has second functional groups. Okay, so the two chain ends is present. Number of number of total chain end is defined as, if you find unreacted A group and unreacted B group, then you can find how many chain ends that we have. If you divide this chain end by 2, because we have two chain ends, then we can calculate the number of molecules of Xmer. So number of total molecules after time t is number of total chain end divided by 2. Number of total molecules n is defined as, number of total chain end, and total chain end is number of unreacted A. Number of unreacted A is Na times 1 minus p. Number of unreacted B is Nb times 1 minus Rp. So if you put this Na 1 minus p plus Nb 1 minus Rp divide by 2, then it comes up with the total number of molecules after time t. And is equal to, if you rearrange them, because we know that the relationship between Na and Nb, Na and Nb is R, feed ratio. So if you put the feed ratio here and rearrange them, then you come up with this equation. So dPn is equal to 1 plus R divided by 2R times 1 minus P plus 1 minus R. Okay? So this equation is 1 over 1 minus P, of course, but if you know the feed ratio, how many molecules of A and how many molecules of B, put it into your reactor, you can calculate the dPn. Assuming that if you have a P is close to 1, then you can cancel this out so that it will become very simple equation. 1 plus R divided by 1 minus R. Let's say that we have a feed ratio which is equal to 1. If feed ratio is 1, dPn will be 1. Okay? Is infinite, because it will be infinite anyway. So if you have equimolar molecules in your system, dPn will be infinite. However, if you have a 1% excess of your and one of the other monomer, 1% excess, that means R is equal to 0.99, because if you put glycerol, number of functional groups is equal to 1, and you have a 1% excess of acid, which is 1.01, it will become 0.99. If you put R is equal to 0.99 here, okay, dPn will become around 200. So 1% of your excess of the second monomer or the first monomer, whatever, you can come up with dPn is equal to 200. It's like a magic. But if you put 1% excess, or you are given in your exercise, you are given, maybe you have a 0.5% excess or 2% excess, what happened? What about the degree of polymerization? Well, you can put your equation here, R, and come up with the different dPns. Okay. So 2% excess will give you about 100. 1% excess will give you about 200. 0.5%, of course, will be about 400 or something like that. So, you can control the molecular weight by using non-stoichiometry. Non-stoichiometry, meaning that you have excess amount of the monomer, put it into your reaction system. You can very easily control your molecular weights. Okay, this is what I can say in English.